like a straight line, and the straight line could be in any number of dimensions, all right? And the number of classes could be any number of classes, right? We are right now trying to understand the concept of VC dimension using just two-dimensional examples or even one-dimensional examples, like we talked about threshold, right? Okay, the thresholding function or the decision stump. Then we talked about intervals, right? And then we also started talking about box classifiers, right? So let us quickly do a quick recap on all of that. And so this is the threshold function. So its VC dimension is 1, all right? And okay, and I hope you have understood the concept of an adversary, right? So let me now talk about interval classifiers. So one point we discussed already in the last class. Yeah, let me start scribbling something. One point we discussed for intervals. Yeah. 2 points. So please speak up. 2 points we discussed. Okay.
Yes.
So now let us talk about 3 points. So if there are 3 points on a real line, can we shatter them using an interval? Okay. So let me draw some points here, right? So one is this. Yeah, so suppose these are 3 points. So if I label them I label all of them as positives, do we have a solution?
Yes, sir.
Yes, sir.
Okay, and if I label them all negative, then do I have a solution?
Yes.
Yeah?
Yes.
Yes, sir. Yes, okay. So now let me give you some situations like the left 2 are negative and right 1 positive. Do we have a solution?
Yes, sir.
Okay, so I'm just trying out some random combinations. Do we have a solution? 2 pluses on the left and then a negative on the right.
Yes, sir.
We have a solution. Okay, so and then if we have negative on the left and 2 positives on the right, do we have a solution?
Yes.
Yes, I can, right, I can do this. But let me now give you a solution, a situation plus, minus, plus. Okay. So do we have a solution for this?
No, sir.
No, right? All right. So right now what we have been doing is that we are enumerating all the possible labelings and trying to see if there are some labelings for which we don't have a solution. So we can see that if the points are labeled like this, right, a negative in between the 2 positives, then we don't have a solution for this problem. All right, getting it? So interval classifiers can, so what can you say about the VC dimension of this? Of interval
2.
classifier? 2, right? So the, right. So all right, so let us do this. So we know that it can shatter 2 points, but it cannot shatter 3 points, because this particular situation gives it cannot give me a solution. Now if I am using interval classifiers, right? So what kind of solution can I propose for this kind of a situation where there are two pluses and in the middle you have one negative? So can you give me a solution for this?
So this will be the union of two sets, union of two
Union
intervals.
union of two intervals?
Yes.
Yeah. So suppose I say that I have a union of two intervals. Say I call them I1 and I2. All right. So if I allow you to have two intervals instead of one, then possibly I'll be able to shatter 3 points. So what I can do is, all of you are able to follow this. Yeah, so I construct one interval here, right? And construct another interval here. All right. So am I able to shatter 3 points? Yes. Because all other cases you were able to do it with one interval, right? So now if I am allowed two intervals, I am able to shatter 3 points. So what about 4 points?
We can shatter 4 points also with two intervals.
Yeah. So all of you are getting this where we are heading, right? So let us see that if I am allowing two intervals, union of two intervals, can I shatter 4 points? So let me give you a case. Okay. So I'm writing here. So let me just okay. Let me just erase these a few of them here. So how to do that? Erase all on the slide. Yeah, all right. So these are from the previous, okay, pen color. Let me use a different color. Okay, right. So suppose now I look at 4 points, right? Okay, so let us see if we can shatter them using union of two intervals. So let me give you a situation: plus, minus, plus, minus. Okay, so can I shatter this particular situation? Yes, we can, right?
Yes, sir.
Yeah, we can. All right. So can you give me a situation for which, using 4 points, for which I don't have a solution? Yeah. Can you think? I mean, just
I
think of.
don't. I don't think. I
Huh.
don't think there is
Yeah.
any, sir.
Yeah. I also I agree with you that we will not have any situation, right? So if I put, I mean, you think of any situation. There are 16 possible labelings. So you can do what is enumerate all of them and then see for yourself, right? But my hunch tells me that yes, I'll be able to shatter 4 points. All right. So now let me take 5 points. Okay, 4 points we are okay. So I'm assuming that we are good with 4 points. All right. So now let me take 5 points. Okay, and two intervals. So let me give you something: plus, minus, plus, plus, minus. Can I shatter this situation or this labeling?
Yes, sir.
We can, right? So two in the one bracket here, right? And one here. So this should also give us some idea about what could be a labeling for which I will not have a solution. What about this one that I just, what about this?
We can't.
We can't, right? So all of you are able to understand this. So 5 points we are not able to shatter. Okay, so VC dimension for two intervals, union of two intervals, is 4, right? All of you agree with that? Yeah, please. No, it is not about rectangle. It is about interval classifiers. We are discussing intervals. Yeah. Okay. So it is all on the real line. So we are talking about points that are on the real line, right? Okay. We are not going to two dimensions as yet. Okay. All right. So you are okay. So I have given you some problems in the problem set, which is which is about two intervals, one interval, right? One interval we have already seen, two intervals we have just seen, right? So what about three intervals, right? Or for that matter, what about union of k intervals? Okay, so this problem I have given you in the problem set. So try to think about what you can do with union of k intervals. So, right? So how many points we can shatter using this?
2k points, I think so. Like,
Uh,
if we
yeah,
go for a lower bound, then
no, like VC dimension, you know the definition of VC dimension, right?
yeah,
Okay,
2k. Yeah.
yeah. So VC dimension is that how many points it can shatter. So like we saw in the case of 2, it can shatter 4, but it cannot shatter 5. So its VC dimension is 4, right? So similarly, if I have k intervals, union of k intervals, how many points I can shatter? So this is like just have to think. So if you have two cases, suppose k is 4, right? Okay. Suppose k is 4. Okay. All right. So k is 4 means I can have 4 intervals, right? So if I just do alternate plus minus, right? Right? If I do this, right? One,
yes, sir.
two, three,
That's
four, five,
7
six,
points.
seven. 7, 8, 8 can I shatter?
Yes, sir.
Okay. So I'll be able to shatter, so I can put a plus here or a minus here, right? All of that I can do, right? Okay. All right. So are you getting this? So if I'm using k union, if I'm using a union of 4 intervals, then I'll be able to shatter 8 points. So it appears that when you have k union of k intervals, you can shatter 2k points. All right. Okay. But this is not a proof, right? So you need to work on the proof. All right. Okay. So can we now move to box classifiers? Okay. So if I have a box classifier, all right. So how many points I can shatter? So box, so these are also like we call it axis parallel box, right? Because the sides of the box or the square are parallel to the axes. So we also call it axis parallel box, right? It could be a square, it could be a rectangle. So let us first talk about a square. So if I have just 1 point, right? So can the box shatter this point? Shatter 1 point? Yeah, so I can construct a box around it. So yes, if my point is negative, then what? I can construct a box which does not contain this negative point, and I'm done, right? And now you have to see that you are now no longer in one dimension. So you are in R squared, right? So now you are in a two-dimensional space, all right? So your points are in R squared. So now let me take 2 points. If both points are positive, then do I have a solution?
Yes,
Yes,
sir.
sir.
Right, I can construct a box that is big enough to enclose both the points, right? I can do that. Yeah. So if both are negative, so I'm discussing all the 4 cases one by one. If both are negative, then
We can't.
we can.
Yes, sir.
Yeah, because I have to just draw a box which does not contain these 2 points, and I can always do that. All right. So when one is positive, one is negative. I mean, it does not matter here that which one is positive and which one is negative, right? You understand this? Yeah.
Yes, sir.
So if one is positive, one is negative. So both the cases I'm considering, which one is positive, which one is negative is not important here. So can I construct a solution?
Yes, sir.
Yeah. So I can always do this, right? Okay, leave out the other point, irrespective of how close it is to the plus point, right? Or how far it is from the plus point, right? And here, while discussing shattering, we are not uh, worried about generalizations, right? Are you understanding this? We are just trying to find a solution that works, right? Okay. We are not going to use this as a classifier, right? Okay. But what we are trying to do is getting some idea about the power or the capacity of box classifiers. All right. So now suppose I have 3 points. Okay. So if I have 3 points, what happens? Yeah.
We can't. Like for the worst case, we can't.
No, worst case, you have to tell me the specific case where we can't.
When we have plus, minus, and then plus in a straight line.
In a straight line, okay. So what you are saying is something like this: plus, minus, and plus, right? So you have something like this in a 2D space. So what you are saying is that all the points have the same y value, right? Right?
Yes, sir.
So y value is same for all of them, and x values are different, so they appear to be on a straight line. So if this is the case, can I draw, or can I have a box which has only positive points inside it and negative points outside it? So you will see that you will not have a point. So 3 points it cannot shatter, right? All right.
Yes, sir.
Okay. So now again, if I give you 2 boxes union, right? So again, now I'm trying to generalize this concept of unions of classifiers, right? So if I give you a union, so then I'll be able to shatter these 3 points, right? Okay. Are you getting this? Okay. So let me introduce a blank slide. Okay, just I'll discard. So because I want to new slide. Okay. Okay. All right. All right. So now, I mean, I somehow I forgot to get my tab. So let me use a pen here. So it takes a little bit longer, but that's all right. So now let me talk about another important concept, right? So you know linear separability, right? Linear separability, you know.
Yes, sir.
Okay, so if I say give you what? Let me give you. So you know the AND gate, right? All of you know the AND gate or the OR gate,
Yes, sir.
right? So draw the AND gate. So if I were to draw the AND gate, so let me see if I can draw it properly. So this is my X1, right? This is my X2. So this is 0. This is 1, right? So this is 1 here, all right? So what happens if, suppose I'm doing OR first. So if both are 0, we are 0, right? If 1 is 0, 1 is 1, I have 1. If 1 is, okay, sorry, it is 0, and this is 1, then again I have 1. And if it is 1, 1, I have 1. So what you see? So if these points I indicate as a cross, right? And this as a circle, right? Not 0, this is a circle. Okay. So which point is a circle? So this point is a circle, right? 0, 0. This point 0, 1 is what? It's a cross. This point is also a cross, and this point is also a cross. All right. So you have these 4 points, and so is the OR gate linearly separable? Yeah, it is, because I can always find a line which goes like this, and it separates the 2 kinds of points. All right. Now if I do the AND gate, right? So AND gate would be what? So AND gate I'm writing, so this is my OR gate, okay, and this is my AND gate here. So what if it is 0, 0? It will be 0. What is 1, 0? 0. 0, 1 is 0, and 1, 1 is 1. So only this point is different. So let me, okay, 0, 0, 0. So this point becomes a circle, and this point also becomes a circle, right? And this point is a cross. Okay. So now, is it linearly separable? AND gate?
Yes, sir.
It is, right? So I can, yeah, so my line goes from here, right? Somewhere, right? Again, I have infinitely many solutions. So both are linearly separable. All right. Okay. So now let me talk about another gate, which is XOR, right? Okay. So do you know about XOR?
Yes, sir.
Yes, sir.
So
If X and Y are different, we get a 1, otherwise 0.
yeah. So let me write down XOR here. Okay. So let me write down XOR here. Okay. So 0, 0 is what? 0. Right. 1, 1 is also 0. And 1, 0 and 0, 1 are these. So if I draw them, what happens? So 0, 0 is 0. So let me put a 0 here. And what is it? No, wait a minute. 0, 0. So this will be 1 and this will be 1, right? And these would be 0. So 1, 1. So if it is 0, 1, so here I have a cross on the axis, right? And 1, 1 would be here, which would be a circle, right? So this is my XOR gate. So is it linearly separable?
No.
It is
No.
not. All right. So let us now look at, I'll go back to the linear line. Okay. So I have points, 3 points in this, on this line. It is hardly linear, looking linear, right? So, but just you'll have to bear with it as I'm drawing it with my mouse, right? So let me give you this situation. Okay. All right. So is this data now? I'm going back to one dimension, right? So this is a one-dimensional case, and this is a 2D case that I'm talking about. So all right. So one-dimensional. So is it linearly separable?
No, sir.
It is not. Right. So how do you define linear separability in case of a linear one-dimensional points? That you can find a threshold function, right? So you know that we have already discussed the threshold function. So you know that it is not linearly separable. Now, what I'm asking you to do is, how can I make this linearly separable? Okay. All right. So let me give you, I mean, this I have discussed in some context, not directly. So this was my X, right? Or X1, I would say, right? Now let me add another dimension, and I call it X2, right? And this is X2 dash in this direction, that is the negative. So this is suppose 0, right? Okay, so this is X2 dash, which indicates negative values or the negative direction, right? Okay, so now what? If I were to make it linearly separable, what should I do? Sorry. So we have added one more dimension, that is x2. Now what we should do to the point, just adding a dimension is not going to help. If suppose y value is 0 for all of them, right? It is not going to help. These points will remain where they are, right? If the
You
x2
can
value
square them.
square, okay? So suppose this value is 2, this is 3, and this is 4, all right? So if I square them, then what happens? Square means you are saying that 2 becomes 4, so the point is here, moves here, right? 3 becomes 9, it point moves here, and 4 becomes 16, so it moves somewhere here, right? Okay, and this is a negative point, right? And these two are positives, right? So they'll be on a hyperbola, right? Okay, so would they become linearly separable?
Yes,
Yes,
sir.
sir.
Now they are not on a straight line,
Not
so
on,
we
they are
can
not on
certainly
a
do that.
straight line, so they are on a parabola. That's what I was telling you. So since they are on a parabola, right? I'm not able to draw it properly, but you understand this, right? So now they become linearly separable, right? All right. So a better way of looking at it, this x square is perfectly fine. So can I find a function, right, which does something like this? That this point, I'm taking this point, you could have taken the other 2 points. If I find a mapping or transformation such that this point moves up, right, other 2 points remain where they are, and I'm just trying to tell you geometrically, right, and or this point moves down. And it's not a matter of by how much, right? You just have to move it from the x-axis, right? So if I either move this point up or down, then this problem becomes linearly separable, is it not? Right. So from one dimension, if I move to two dimensions, is it not? Have you understood this? Yes or no?
Yes, sir.
So the what we have done, so if there are points in on a one-dimensional line, or if we have one-dimensional points which are not linearly separable, right, we can possibly make them linearly separable by mapping them to a higher dimensional space, right? So in this case, I am mapping them to a two-dimensional space in such a way that one of the points, like which is differently labeled than the other points, moves up or down. Once I do that, I'm done, right? Okay. So moving to a higher dimensional space is one solution, and this is what we typically do in the kernels, right? When we were discussing SVM, right, we discussed this concept that you take the points to a higher dimensional space using some nonlinear mapping, which is phi, and then you hope that you have done the job. So in this case, what kind of mapping I could think of is phi x. It takes a point, a one-dimensional point x, and does what to this? So x comma x squared. Is that fine? So I have moved the point from one dimension to two dimensions. And this is how I define my mapping. Are you okay with this?
Yes.
Okay. So now are you able to link it to what we were trying to do in SVM and the concept of kernels? Right? Okay. So all of these concepts come together. Right. So now let me talk about another very important concept. Right. Say, okay, so you were seeing while discussing VC dimension that one line or one threshold or one interval is not going to solve this problem, which is shown here, right? So I'm again drawing it. Okay. Okay, let me not draw it like this. So I'll simply write down the labels. Right. So one interval is not going to solve this problem, but two intervals are going to solve this problem, right? Okay. So one way is that you transform these points to a higher dimensional space and then talk about kernels and this nonlinear mapping and all of that stuff, right? One way is that. Let me now hint you or give you a hint about another kind of solution that we can think of, right? Without going to a higher dimensional space, okay? So instead of one interval, I'm using a union of two intervals. So is it solving the problem?
Yes, sir.
Yeah. So now similarly, so let me introduce one more slide, or let me just erase all of this. Yeah. So let me choose a pen again. Okay. So now let me take you back to the XOR case. Okay. So what we had was 2 points which are same and 2 points which are, I mean, 2 are crosses and 2 are circles, right? This is what is XOR. So is this linearly separable? So we say that it is not. So that means what? Using one line, I cannot separate the two kinds of points, right? Okay, so if I now talk about a line, so if I draw one line, if I take one line, any orientation, right, is it able to solve the problem? One line would be able to separate the two kinds of points? The answer is no, right? Because this is not linearly separable data. But if I now say that instead of using one line, you use two lines, yeah? If I tell you this, then what happens? Are you able to solve this problem?
Yes, sir.
Right, so let me draw two lines, right? Any two lines. So one is this and one is this. So is it similar to what we were discussing in terms of union of intervals? Yeah,
Yes, somewhat similar.
somewhat similar in the sense, the concept, like just one interval or two intervals, one line or two lines, right? So you can see that the capacity of two lines would be more than the capacity of a single line. You understand this?
So we can also say the flexibility and the complexity increases, right?
Yeah, definitely. I mean, right now I'm focusing on capacity because that's what VC dimension talks about, but capacity, flexibility, complexity, everything is same. I mean, all these concepts are same, right? I've told you this already. Like even if you look at it in terms of the parameters, right? So one line would have how many parameters? 3, right? W1, W2, and B, right?
Yes, sir.
What is, right? 3 parameters, W dot X plus B in 2-dimension space, right? Is equal to 0, right? That is what is your line, right? So how many parameters? 3 parameters. Now if you have 2 lines, how many parameters? Yeah,
6.
6 parameters. So when the number of parameters increase, you can see the complexity increases, is it not?
Yes, sir.
So it's a very simple concept. Similarly, if you have one interval, right? How many parameters?
2
Two
parameters.
parameters.
2 parameters, right? All right. So if I have 2 intervals, then how many parameters?
4.
4, right? So 2 more. So 2 plus 2, 4. So this is a more complex model. There's no doubt about it, right? As compared to one interval. 2 interval is a more complex model, right? Because you have to tune 4 parameters, or you have to find 4 parameters, right? And similarly, in the case of lines, when you have just one line, you have to find 3 parameters. When you have 2 lines, you will have to have 6, you have to find 6 parameters, right? All right. So are you now getting that when I take the union of classifiers, right, I'm able to solve more complex problems. All right. I'm able to solve more complex problems, which were otherwise not possible using just one line or one interval, right? Or for that matter, one box, right? So if I'm allowed 2 boxes, then I can solve more complicated problems, right? Okay. So is this concept you are able to appreciate? Okay.
Yes, sir.
All right. So now let me link this whole thing. So how many of you know perceptrons? I'm now taking you, now not taking you right now there, but I'm now trying to introduce neural networks. All right.
Yes, sir.
So what is the simplest neural network that you know? So if you have background, and if you don't have background, don't worry, right? So let me tell you about a perceptron model, right? I'll not mathematically talk about it right now. Okay, so let me talk about a perceptron model. Okay, so what it does, so perceptron model is nothing but a linear classifier, which means that it's a single straight line or a plane, right, or a hyperplane. That's it. So, and it can be used to solve problems, two-class classification problems, which are uh, uh, linearly separable, right? So a perceptron would be able to solve your OR gate problem. It will be able to solve the AND gate. So I'll just use or AND, right? Right? But it will not be able to solve XOR, right? So it will not be able to solve XOR, but it will be able to solve OR. It will be able to solve AND gate for you, right? Okay. So now what we do is, right? So the perceptron model, as I said, it is nothing but a line, right? Okay. So you are given some data in space, okay, and you are given a line or a hyperplane depending upon what is the dimension of the space that you are working in, right? And then you will be given a line which is an initialization, right, an initial line, and then you'll have to learn, right, okay, and rotate this line in any way you like so that it fits the data. That's what you do in perceptron, but you have just one line. Now when we talk about uh, a problem like XOR, so we have just seen that one line is not going to be enough. You need two lines, right? So this two lines is, the second line is corresponding to a layer in a neural network, right? Okay, so perceptron is also called as a single layer perceptron or single layer neural network. And then we have this concept of a multi-layer neural network. All right, so are you getting this? So a layer, when you add a layer to a neural network, you are able to solve more complex problems, right? And if you keep on adding layers to a neural network, you are possibly building capability to solve more and more complex problems. And that is what takes you to deep learning models, right? Where you have too many layers in that, right? So that is what is deep learning, right? So you start off with the simplest model, that is a single line, right? Then you add more lines, right, as the problem becomes more complex and when the data is not linearly separable, and then you keep on adding layers, right? So that is what is an introduction to neural networks. So I'll be taking it up probably in the next class, right? So I hope you have understood this. So any questions on what I discussed today? These are
Sir, could you once again explain, show how you got that XOR graph? XOR?
XOR graph is that if you have just one out of the two, right?
1 means it is 0.
You will get a 1. 0 1 1 0 would be 1, right? And if it is both 0, it is 0, and it's both 1, it is 0. Okay?
Both 1 it is 0. Both 0 it is 1, right, sir?
Yeah. No, both 0 is also 0.
Okay.
Okay, so all right. Okay.
Excuse me, sir.
Yeah.
So I have a doubt that why is the straight line supposed to have 3 parameters? Like we can have just one slope and intercept. There should be just 2.
See, okay, so this actually w dot x plus b, right? So what we write it as w1 plus w1 x1 plus w2 x2 plus b, right?
Yes, sir.
Okay. So it doesn't matter, say these are different. So in vector form, we typically write it like this, right?
Sir, we can
Yes.
just divide this equation by W2 and we'll still have.
Aha, we can do all of that, right? So it doesn't matter. Are you getting this? So this b can become a part of the of your w vector itself, right? This can be absorbed.
Yes, sir.
All
So
right.
what should we assume? Like it should have 2 parameters or
So
3?
two and three both are correct.
Okay,
Okay.
sir. Okay, sir.
No issues with that. Yeah. Only thing what we are discussing here is that if you have 2 lines, the number of parameters would double, right?
Yes, sir. Got that
That's
one,
the
but
only.
I had it out in
Yeah.
this one.
Yeah. That's fine. Yeah.
Okay, sir.
All right.
Thank you. Yes, sir.
Okay, and I'll also post something on some project project type courses. We have a new lab in the department now, so I'll post it on Nalanda. So on the course website. So if you are interested, you can apply. There's a small form that you have to fill, and you can also share it with your friends who are interested. All right. So I'll do that. Okay.
What's the lab for?
It is we are calling it Disruptive Technologies Lab. So it talks about AI ML, it talks about IoT, it talks about blockchain, right? 3
Yes.
technologies we are focusing on right now. All right, so I'll close the class and you look at the problem statement or problem set 2, and I'll also put up some project openings on Nalanda, right? Okay.
Okay,
Thank you.
sir.
Thank you.